Good morning, friends. I am Vikas Kumar, Assistant Professor, Department of Chemistry, MS College, Saharanpur. In today's class, we will discuss about symmetry elements and operation in group theory. In today's lecture, first we will discuss about what is symmetry, and after that we will discuss about symmetry elements and operation, and in last we will discuss types of symmetry elements. In this slide, we will discuss about what is symmetry. Symmetry is the quality of being made up of similar parts arrangement around an axis. Or as we are chemists, we can also say it is regular arrangement of atoms or groups in the molecule or an object. In this example, we can see two objects. First is symmetric and second is asymmetric. And both sides of this axis having regular pattern, and in this one side of axis having regular pattern, but other side this pattern is irregular. We can say this is symmetric object and this is asymmetric object. We can also see the symmetry in isomers of 2-butane. First is cis-2-butene and second is trans-2-butene. Cis-2-butene is more symmetric than trans-2-butene due to the both CH3 are present upside to this double bond, and in this case one CH3 is above and one CH3 is below. In these molecules we have more regular arrangement of groups, and in this case we have an irregular arrangement of groups around CC double bond. And symmetry is omnipresent in world. We can see symmetry in living being. Also symmetry is present in architecture, even in molecules. We can see symmetry in animals. We can see symmetry in architecture, and we also see symmetry in molecules. In this slide, we will discuss what is symmetry element and operation. Symmetry elements are geometrical entities like axis, plane, or point that can be used to analyze the symmetric property of an object or molecule. Means symmetry elements are geometrical entity. It may be axis, plane, or points around which we can perform symmetry operation. And what is symmetry operation? Symmetry operation is the movement on the molecules in order to get an equivalent or indistinguishable configuration or orientation. Symmetry elements or symmetry operation we can easily understand with the help of water molecules. In water molecules, we labeled hydrogen as HAHB, for understanding, but both of hydrogens are identical. We passes a imaginary line through oxygen atom, and this imaginary axis is called symmetry element. Around which around 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 this imaginary axis we perform a symmetry operation, that is rotation. And when we perform rotation of 180 degree around this imaginary axis, we convert this original configuration into equivalent or indistinguishable configuration. And when we perform this operation second time, we get identical configuration. In this slide, we will discuss types of symmetry elements or operation. First symmetry operation is reflection, denoted by sigma, and it is related with symmetry element plane of reflection. Second symmetry operation is rotation, denoted by Cn, and is related with axis of symmetry or axis of rotation or rotational axis. And third symmetry operation is improper rotation. It is denoted by Sn, and this symmetry operation is related with rotation followed by reflection symmetry element. And another symmetry operation is inversion, denoted by I, and it is related with symmetry element center of inversion. And last one symmetry operation is identity. It is related with symmetry element E itself or doing nothing. So first we will discuss about identity. This element is obtained by operation, as we earlier said. This is identity operation. This is doing nothing in molecules, and after this operation a molecule remains same. In this example we can see this is our original configuration. After applying operation identity, it remains same. This situation can be visualized by two ways. First is we do not do anything on the molecules, or we rotate the molecules by 360 degrees. Every molecule has this type of symmetry elements or symmetry operation. This is denoted by symbol E. Second symmetry element or operation is axis of rotation. This is symmetry element, and symmetry operation is rotation. It is also called it rotational axis of symmetry. Axis of symmetry or rotational axis of symmetry is an imaginary axis passing through an object or molecules, rotation on which by theta degree provide equivalent or indistinguishable orientation or configuration. It is denoted by Cn, where n is the order of axis, and this rotational axis is called it n-folded rotational axis, where n is equal to 360 degree divided by theta. Means if we rotate an object around its imaginary axis, by 360 degree, then we get n is equal to 1, and we can say this imaginary axis is one-fold rotational axis. And when we rotate an object around imaginary axis by 180 degree, then we get n is equal to 2. And in this case, we say this rotational axis is two-fold rotational axis. When theta is 120 degree, then n is equal to 3. And in this case, the rotational axis is three-fold rotational axis. And in the case of when theta is 90 degree, then n should be 4. And in this case, our rotational axis is four-fold rotational axis. Axis of symmetry can be simplified with the example of water molecules. Actually, water molecules contain one C2 axis passing through oxygen atom and interchanging H1 and H2 with each other. In this case, when we rotate water molecules around this imaginary axis by 180 degree, we get this equivalent orientation in which H1 interchange by H2 and H2 interchange by H1. And when we perform this operation further, we get identical orientation, and this 2C2 means 2 times two-fold rotational axis apply on the molecules. Means MCN means M times N folded rotational axis. Second example is BF3. In the case of BF3 molecules contain one C3 axis passing through boron atom and is perpendicular to triangular plane and interchanging fluorine atom F1, F2, F3 with each other. When we apply C3 first time, then F1 interchange by F3, F3 interchange by F2, and F2 interchange by F1. And this rotation is clockwise rotation around C3 axis by 120 degree. When this operation apply further, we get this orientation, and when C3 further apply, then we get this type of orientation. In case of BF3, as we see, BF3 contains one CH3 axis passing through boron atom and perpendicular to triangular plane and interchanging all F atoms F1, F2, F3 with each other. BF3 also contains three C2 axis passing through each BF bond. First is C2, second is C2 dash, Third is C2 double dash. These axes interchanging other C2 other fluorine atom with each other. When we will discuss C2 means C2 is passing through BF1 and these imaginary axes interchange F2 and F3. When we apply this to the molecules, we will we get this type of orientation, and when we further apply it to the BF3 molecules, we will get last orientation in the case of BF3 molecules. Rotational axes can be classified into categories. First is principal rotational axis and second is subsidiary rotational axis. Axis of highest order is defined as principal rotational axis and axis other than principal axis is called it as subsidiary rotational axis. Both rotational axes can be understand with the example of NH3 molecules. In NH3 molecules, NH3 molecules contains one C3 rotational axis and three C2 rotational axis. C3 rotational axis passing through nitrogen atom and it is perpendicular to the triangular plane and interchanging H1, H2 and H3 and C2 axis passing through each NH bond and interchanging other. If we take this C2 passing through an H1 atom, this interchange other H atom means H2 and H3. In this case, we in this case NH3 molecules have one C3 axis and three C2 axes. C3 axis having highest order, this is called it principal rotational axis and C2 is called it subsidiary rotational.